Hello students, welcome to this lecture, One Real Numbers. So in today's lecture, basically we'll discuss recall, then we'll discuss some examples, then we'll discuss exercise 1.2 from NCERT class 10 books. Okay, then we'll summarize whatever covered in this lecture. Okay, so in class 9 you have studied is two important properties. Okay, sum or difference of a rational number and an irrational number is irrational. Okay, so if we have rational number r and irrational number s, then r plus s or r minus s, this is irrational numbers. Okay, so sum or difference of rational numbers and an irrational number is irrational number. Okay, so this property is very important property for all of you. Okay, suppose you have given irrational number root 2. Okay, so we have already proved root 2 is irrational number. Okay, and if we take rational number 2, okay, then if we sum them 2 plus root 2, this number is basically an irrational number. Okay, or if we take difference 2 minus root 2, this is also an irrational number. Okay, and second property, the product and the quotient of a non-zero rational and irrational number. So here non-zero is very important thing. Okay, so the product and quotient of a non-zero rational and irrational number is irrational. Okay, so if r is rational and s is irrational, then r times s, is the product of r and s, is irrational. Okay, and r divided by s is also irrational number. It will happen when we take non-zero rational number and irrational number. Okay, now other than if we take zero rational number, if we take r equal to 0, okay, then 0 times s, this is equal to 0, and 0 is a rational number because 0 can be written as 0 over 1, 0 over 2. That's 0 can be expressed as a fraction a over b, where b not equal to 0. Okay, so if we take 0 rational number, then the product will rational number. Okay, so here this is why we take non-zero, rational and irrational numbers. Okay, then the product and the quotient of a non-zero rational number and irrational number is irrational number. Okay, so we proved some particular cases here. So in our previous class, we have proved some particular cases like root 2 is irrational number, root 3 is irrational number, 2 plus root 5 is irrational number. Okay, so here in this example, here we have to show that 5 minus root 3 is irrational number. So student, how can you prove that 5 minus root 3 is irrational number? Okay, so you can prove 5 minus root 3 is irrational number by using method of contradiction. Okay, so you all know about method of contradictions. Okay, so here for proving 5 minus root 3 is irrational number, here first let us assume to the contrary that 5 minus root 3 is rational number. Okay, so here first we assume 5 minus root 3 is rational number. So that is, now we can find co-prime numbers a and b. Since 5 minus root 3 is rational number, so we can find co-prime a and b where b not equal to 0. Okay, such that 5 minus root 3, this can be written as a over b where b non-zero. Okay, so therefore if we rearrange this equation, 5 minus root 3 is equal to a by b, then we get 5 minus a over b. This is equal to root over 3. Okay, so 5 minus a over b, this is equal to root over 3. So here if we rearranging this equation again, then we get root 3, this is equal to 5 minus a over b, and this is equal to 5b minus a over b. Okay, and since a and b are integers, so this fraction a over b is rational number and 5 is rational number, then difference 5 minus a over b is also rational number. Okay, so in right hand side we have 5 minus a over b, this is a rational number. Okay, so it implies root 3 is rational number. So is root 3 irrational number? But we have proved in our previous lecture root 3 is an irrational number, that we have already proven. Okay, so in our previous lecture, so here this contradicts the fact that root 3 is a rational number. Okay, so this contradiction has arisen because of our incorrect assumption that 5 minus root 3 is rational number. Okay, so our assumption 5 minus root 3 is rational number is basically incorrect. That is why this contradicts the fact root 3 is irrational number. Okay, so we conclude that 5 minus root 3 is irrational number. Okay, so initially we assumed 5 minus root 3 is rational number. Okay, then at the end of this proof, here we get this contradiction, the fact that root 3 is irrational number. Okay, and this contradictions has arisen because of our incorrect assumptions that 5 minus root 3 is rational number. Okay, so and then we conclude that 5 minus root 3 is irrational number. Okay, so now let us move to next example. Okay, so in next example, here we have to show that root 3 times root 2 is irrational number. Okay, so we here also use the method of contradiction to prove 3 times root 2 is irrational number. Okay, so let us assume to the contrary that 3 times root 2 is rational number. Okay, so 3 times root 2 is rational number. So we can find co-prime integers a and b where b not equal to 0, and we can write 3 times root 2, this is equal to a over b. Okay, since 3 times root 2 is rational, then we can express 3 times root 2 as a fraction. Okay, so we can find co-prime numbers a and b where b not equal to 0, and such 3 times root 2 is equal to a over b. Okay, so now if we rearranging this equation 3 times root 2 is equal to a over b, then we get root 2, this is basically equal to a over 3b. Okay, so we get root 2, this is equal to a over 3 times b. So since here 3a and b are integers, okay, then the fraction a over 3b is also rational. Okay, so a over 3b is a rational number, and so root 2 is also rational number. But we have proved in our previous lecture root 2 is irrational number. Okay, so this contradicts the fact that root 2 is a rational number. Okay, so we conclude that 3 times root 2 is irrational number. So we conclude that 3 times root 2 is irrational number. Okay, now let us move to another example. So in this example, here we have to prove that root 5 is irrational numbers. Okay, so in our previous lecture, we have proved root 2 is irrational number, root 3 is irrational number. Okay, and now we have to prove that root 5 is irrational number. Okay, so now let root 5 is a rational number. So our proving strategy is basically here we will prove by method of contradiction. Okay, so here first let root 5 is a rational number. So since root 5 is a rational number, then we can find two integers a and b where b not equal to 0, and such that root 5 can be written as a over b. Okay, so first you have to let root 5 is a rational number, and therefore we can find two integers a and b where b not equal to 0, such that root 5 this is equal to the fraction a over b. Okay, so let a and b have a common factor other than 1. So if a and b have a common factor other than 1, then we can divide them by the common factor. Okay, and we assume that a and b are co-prime. That means the GCD of a and b is equal to 1. Okay, that means a and b have no common factors other than 1. Okay, so only a and b have 1 as a common factor. So a and b have no other common factor other than 1. Okay, so here we let assume. So now we rewrite and rearranging the equation, then we can write a this is equal to root 5 into b. Okay, so a this is equal to root 5 into b, and now if we squaring both sides, then we'll get a square this is equal to 5b square. Okay, so a square this is equal to 5b square. Therefore here a square is divisible by 5. Okay, since a square is equal to 5b square, so therefore a square is divisible by 5. That means 5 divides a square. Okay, so it can be said that a is also divisible by 5. That is basically by previous theorem that we have discussed in our previous lecture. Okay, so in our previous lecture we have discussed this theorem. So theorem, what is that theorem? Let p be a prime number. P be a prime number. P divides a square. Then P divides a. Okay, where a is a positive integer. So P be a prime number, P divides a square, then P divides a, where a is a positive integer. Okay, so if we use this theorem, then here a square divisible by 5, so it can follows that a is also divisible by 5. Okay, so since a is divisible by 5, then let a this is equal to 5 times some integer k. Okay, so a is equal to 5 times k, where k is an integer. Okay, now if we squaring, then 5k square this is equal to 5b square. Okay, so 5k square this is equal to 5b square. This means that b square is divisible by 5. Okay, and by this theorem b is divisible by 5 also. Okay, so now b square is equal to 5k square. This implies that a and b have 5 as a common factor. Okay, so a and b have 5 as a common factor, but this is a contradiction to the fact that a and b are co-prime. That means a and b have no other common factors other than 1. But here we get a and b have 5 as a common factor. Okay, so this is a contradiction to the fact that a and b are co-prime. Okay, so basically this contradiction has arisen because our assumption, the assumption that root 5 is a rational number, is wrong. Okay, so hence we conclude that root 5 cannot be expressed as a p over q, or it can be said that root 5 is a rational number. Okay, so root 2, root 3, root 5 are all irrational numbers. Okay, so now we have to prove that 3 plus 2 times 5 root 5 is irrational. Okay, so we have to prove this number is irrational number. Okay, so here this number 3 is rational number, and we know root 5, this is irrational number that we have proved in our previous slide. Okay, so root 5 is irrational number. So 3 plus 2 times root 5, this is irrational number. Okay, so but here we prove it by method of contradiction method. Okay, so first let 3 plus 2 times root 5 is rational number. Okay, so we let 3 plus 2 times root 5 is rational number. So therefore we can find two integers a and b where b not equal to 0. B is not equal to 0. Okay, such that 3 plus 2 times root 5, this is equal to the fraction a over b. Okay, so 3 plus 2 times root 5, this is equal to a over b. And now if we rearranging this equation, 3 plus 2 root 5 is equal to a over b, then we can write 2 times root 5, this is equal to a over b minus 3. Okay, and now if we divide whole equation by 2, then we get root 5, this is equal to 1 over 2 times a over b minus 3. Okay, so here a, b, 3, 2 are all integers. Okay, so 1 by 2, this is rational number. A over b, this is rational number. 3 rational number. So in the right hand side, this number 1 by 2 times a over b minus 3, this is rational number. Okay, so 1 by 2 times a over b minus 3 is a rational number. So it implies root 5. So it implies root 5 is rational number. But in our previous slide, we already proved that root 5 is irrational number. Okay, so this contradicts the fact that root 5 is a rational number. Okay, so hence our assumption that 3 plus 2 times root 5, 3 plus 2 times root 5 is rational number is false. Okay, so this is false. So therefore, we conclude that 3 plus 2 times root 5 is irrational number. Okay, so 3 plus 2 times root 5 is irrational number. Now let us start question number 3. So here we prove that the following are irrational number. Okay, so first one we have 1 by root 2. Okay, so 1 by root 2, this is irrational number. So how can we prove it? So here we can let 1 by root 2 is rational number. Okay, so therefore we can find two integers a and b where b not equal to 0, such that 1 by root 2 can be written as a over b. Okay, and it implies root 2, this is equal to b over a, and this is possible when a is non-zero. Okay, so root 2 is equal to b over a. Okay, so b over a, this is rational number since a and b are integers. Okay, so b over a, this is rational number. So therefore root 2 is also rational number, but which contradicts to the fact that root 2 is a rational number. Okay, so root 2 is irrational number. This contradicts the fact that root 2 is irrational number. So our assumptions 1 by root 2 is rational number is false. Okay, so by method of contradiction, therefore 1 by root 2 is irrational number. Okay, good. I hope you got it, this point. Now let us move to next one. So here we have to show 7 times root 5. This is irrational number. Okay, so we first let 7 times root 5. This is rational number. Okay, so therefore we can find two integers a, b, where b not equal to 0, such that 7 times root 5, it can be written as a over b for some integers a and b. Okay, now if we divide this equation by 7, then we get root 5. This is equal to a over 7b. Okay, so therefore we get this equation root 5, this is equal to a over 7b. So here a, b, 7 all are integers. Okay, so a over 7b, this is actually rational number. Okay, so a over 7b is rational number where a and b are integers. Okay, so therefore root 5 should be rational number. Since root 5, this is equal to basically a over 7b. Okay, so root 5 is rational number. But in our previous slide, we proved that root 5 is irrational number. Okay, so root 5 is irrational number. So this contradicts the fact that root 5 is irrational number. Okay, so this contradicts the fact that root 5 is irrational number. So therefore our assumptions 7 times root 5 is rational is false. Okay, so hence 7 times root 5 is irrational number. Okay, so 7 times root 5 is irrational number. Now we have to prove 6 plus root 2 is irrational number. Okay, so here let us consider by the contrary that 6 plus root 2 is rational number. Okay, so therefore we can find two integers a and b where b not equal to 0 such that 6 plus root 2, this is equal to a over b. Okay, and if we rearrange this equation, then we get root 2, this is basically equal to a over b minus 6. Okay, so root 2, this is equal to a over b minus 6. And since a and b are integers, then a over b minus 6 is also a rational number, and hence root 2 should be rational number. But this contradicts the fact that root 2 is irrational numbers. Okay, so therefore our assumption 6 plus root 2 is rational number is false. Okay, hence 6 plus root 2 is irrational number. Now we summarize whatever we covered in this chapter. So in this chapter you have studied the following points. First point is the fundamental theorem of arithmetic. It's stated to us every composite numbers can be expressed or factorized as a product of primes, and this factorization is unique. Okay, apart from the order in which the prime factors occur. Okay, and second, we have studied about this theorem. If p is a prime and p divides a square, then p divides a. Okay, so if p is a prime and p divides a square, then p divides a, where a is a positive integer. Okay, so a is a positive integers, and here to prove that root 2, root 3 are irrational number. Okay, and in our initial lecture we have discussed about HCF, LCM. Okay, so there we have discussed about these two terms. So HCF is basically in full form highest common factors. Okay, so HCF between two positive integers, basically the highest common factors between them which is highest. Okay, so HCF between two numbers we can find by prime factorization method. So basically we first factorize two numbers, prime factorize two numbers. Okay, then we get some prime factors. Okay, and among these prime factors which is common in both, and we take them and we take basically lowest power of common prime factors. Okay, that is product of lowest power of the common factors is called HCF of two positive integers. Okay, and LCM is basically the product of highest power of the factors in the numbers. Okay, so LCM is basically highest power, product of highest power of the prime factors in the numbers. Okay, and there we have known about this important result. HCF of two numbers a comma b. This is multiplied by LCM of a comma b. This is equal to product of a into b. Okay, so we have studied about this important result. Based on this result, we solve many problems. Okay, so and then we have shown we have seen this result. HCF of a b c times LCM of a comma b comma c does not equal to the product a into b into c. Okay, so by an example we have shown this does not hold. Okay, so for three positive integers, HCF of that three positive integers into LCM of three positive integers does not equal to the product of three numbers. Okay, that we have discussed in our previous lecture. Okay, and this is actually we have discussed in our previous lecture where p, q are positive integers. Okay, and here on more important note, LCM of p, q, r, this is basically equal to p times q times r times HCF of p, q, r divided by HCF of p, q into HCF of q, r into HCF of p, r. Okay, and HCF of p, q, r, this is equal to p into q into r into LCM of p, q, r divided by LCM of PQ into LCM of QR into LCM of PR. Okay, so here we solve some problems. Okay, so here there are some multiple choice questions. So in first question here we have to so these numbers, which types of number is this? Okay, so 2 times root 3, this is basically an irrational number. Okay, this is actually irrational number. Since 2 is rational number, root 3 is irrational number, the product of an irrational number and a rational number is basically irrational number. Okay, so 2 times root 3 is an irrational number. So here option C is correct option for this question. Okay, so let us move to another one. The product of a non-zero rational and irrational number is always irrational number. Okay, so the product of a non-zero rational number and irrational number is always irrational number. Okay, so here option A is correct option. And in question 3, which of the following will have a terminating decimal expansion? Okay, so terminating decimal expansion will have, among them, you have to check. Okay, you have to find the decimal expansion of these 4 numbers, and then we'll see which number the terminating decimal expression will happen. Okay, so and in question number 4 here, if x is equal to 0.7 bar, then we have to find 2x is what? Okay, so basically this number 0.7 bar, this is actually equal to 0.777 dot dot dot. Okay, and if we multiply by 2, then you will get your answer. Okay, that is actually equal to 1.4 bar. So I stop here this lecture. Thank you very much to all of you.